Good evening, all. Welcome back. We are just about to start our day 4. Let's review what we are going to learn today. Yesterday, we saw a regression example where we predicted a continuous variable using linear regression. Today, we are going to see classification using two algorithms. One is logistic regression, the other one is decision tree. Uh, Definitely a lot of topics today. I'm not sure whether we will be able to cover both of them. Let's see how much fall into tomorrow's class as well. So yeah, by end of tomorrow, we can definitely complete trees, and then the day 5 agenda is going to be clustering. So with that, let's jump into logistic regression. I'm going to use the same format that we used yesterday. First, let's run a logistic regression and predict using the logistic regression. Then we will dive into what's the science behind it, how logistic regression is trying to learn, what is the mathematical computations that's happening behind the scenes. Okay, so first let's understand logistic regression, how to perform it with Python, then we will see the math behind it. To start with, I don't need to introduce you to these modules anymore. You're already familiar with it. Pandas, NumPy, Matplotlib, Seaborn. These are some of the modules that we would be using throughout any exercises that you have to do, irrespective of what model you are going to build. Either you are going to use linear regression or logistic regression or decision trees. Data processing is going to be always with the help of pandas, and some functions from NumPy we will always use them. Visualizations, some of the visualizations that we built yesterday using Matplotlib, Seaborn. So these are essential modules for every exercise that we are going to do. Fetch the function called logistic regression from sklearn.linear model. Yesterday we wrote a similar statement from sklearn.linear_model import linear regression. So both linear regression and logistic regression are part of this sklearn.linear_model. Now we built a logistic regression model. We need to assess, we need to test how good the logistic regression model is. So we need some performance metrics for that. Yesterday for linear regression, we used the performance metrics like mean absolute error, mean squared error. We wrote a custom function for MAP, etc. Today for logistic regression, we are going to use something called as accuracy score and another one called confusion matrix. So these two would tell us how good a logistic regression model has learned from the historical data and how does the predictions look like. So that's to start with. Let's read the data. We have a different data set today. I have already uploaded it so that we can save time. So you could see the name of the file credit.csv. So we're going to use this credit.csv here to build a logistic regression model. Let's see what data we have in this credit.csv. There are a few columns. So that's why the variables looks like checking balance. This is already divided into categories. Checking balance, think of this as a kind of current account. Less than $0 per month, $1 to $200 per month, greater than $200 per month, unknown. So the usage of the account is already divided into these four categories: less than $0 per month, 1 to 200, greater than 200, unknown. Duration of the loan in months. So if a customer has, these are all loan accounts, by the way, and we are going to predict if the customer is going to default the loan or not. So the end variable here, default, which says yes or no, this is the target for us. We are going to learn how to predict this. Now, to predict if a customer is going to default the loan or not, of course, we need to learn from the historical data using using the information about the customer, like what's the duration of the loan, how many months the customer has agreed to pay up the loan in terms of installments. What is the amount? What's the loan amount that they have taken? Savings balance, typical monthly savings balance. You see some random values here, like less than $100 per month, greater than $100 to $200 per month. Again, some categories here. Employment duration, how long that person something, etc. Okay, percentage of income, maybe the amount of loan in terms of percent of income, maybe 4% of their overall income, 2% of their overall income. Years at residence, how long they have been staying at the place that they have been, the address that they have provided. Age, other types of credit if they have. Housing, do they own a house or do they rent it or something. Existing loans, if they already have any existing loans. Job type, skilled employee, unskilled, dependents, number of dependents. uh, do they have a phone number? Yes or no? This is probably a very old data set, maybe in the 1980s. So that's why you probably see a lot of no for phone, and we are just going to learn from it. So it doesn't really matter whether it is the latest data or very old data. From these variables, we need to predict, we need to learn how we can predict this, whether a person is going to default or not. Okay. To start with, always start with exploratory data analysis. Why? We need to understand if there is a relationship between the input variable. Let's take duration of the loan. Duration of the loan is an input variable and default is a target variable. Now, do you think duration of the loan will have any impact on a person paying up the loan or defaulting the loan? And put the duration of the loan as, let's say, 6 months. But when you take only 6 months, that means your EMI is more. You are probably having difficulty in paying it. In one of the months, you started defaulting it. It can happen. Second, you might be taking a loan for a very lengthy duration. That means you know that your income, your earnings are not going to be stable. So that's why you want a loan that is very lengthy in duration. That is also a risk, right? Now, is there a relationship between month loan duration and default. How do we know this? So we have to figure that out. If you remember the rule that I told during the visualization class, one of them here is a continuous variable. Loan duration is a continuous variable, numeric, and default or not a default is discrete. So that falls into this particular category. Like gender versus weight. Weight is a continuous variable and gender is a discrete variable. Here loan duration is a continuous variable for us and default is a discrete. Now let's try to see how we can build that plot and what we understand from the plot. Sorry. SNS dot box plot. If you want to know the help, details, what should be there on x-axis, y-axis, etc. Now x is equal to default, and on y-axis we are going to put months loan duration, and data is equal to credit. Somewhere we made a mistake. Equal to months loan duration. Oh, it's data. Okay, it produced a plot. Now look at the boxes here. What did I say about a box plot? That middle line here is the median. When customers are not defaulting, look at the median. The median is maybe somewhere around 20, just little below 20 months, maybe 18 months. When customers are defaulting, this is the duration for customers who are defaulting, and the median duration is just a little about 25. So customers who are not defaulting, their duration is typically less. Customers who are defaulting, yes, their duration is typically more. So that tells us, yes, there is a relationship between the loan months duration and whether they are going to default or not. Similarly, let me do it for another column, and I will comma y is equal to amount, loan amount. Do you think loan amount will also have impact on whether a person defaulting or not? Of course it does, but let's check it out. We can only guess. It may be true or it may not be true. So you have to verify that from the data. Now look at the median of loan amount for non-defaulters. It's just below 2,500, and the median for defaulters is also more or less same, not much difference. And you see after the boxes, after the whiskers, some dots. So that means there are some extreme observations in the data. You can call them as outliers, people who took a huge amount as loans. So those are those dots. Okay. So this is how you try to understand the relationships between the data. And this is a relationship between a continuous variable and a discrete variable. Now let's try to understand the relationship between a discrete variable with our target variable. Let's take this for example here. Checking underscore balance. It's a discrete variable, and we are going to compare and see if there is a relationship between default or not. Two discrete variables. So what should be the graph for two discrete variables? if you remember our graph section, two discrete variables. This is a bar chart that we have used for two discrete variables. Gender separately, survived, not survived. If we take the Titanic example, we want to see if the ratio of people survived are see if the ratio of people who have defaulted is same across different categories of checking balance. If it is same, then checking balance has nothing to do with a person defaulting the loan. If it is not same, then checking balance is important in deciding whether a person is going to default or not. So on X, I am going to use checking underscore balance and look at the type of the plot. Previously, we have used box plot because one is a continuous variable, other one is a discrete variable. Now both are discrete variables, so we need to produce a bar chart. So we used Q is equal to default count plot, which is nothing but the bar chart. Data is equal to data. Ideally, we should not have used the name data for a data frame. That was probably a mistake from my side because it's generally a keyword that is present in Python, and not good to use keywords as names any point in time. So let's change that to df. Now that's good. That looks good. Now when people say data is equal to data, they get confused. So what is this data is equal to data? One of them is a keyword, the other one is a data frame name. So that's not good. So let's say dodge is equal to false. Look at the ratios of defaulting in each of the groups. Less than $0 per month. A very large number of them. So that means the proportion of people defaulting when the checking underscore balance is less than $0 per month is way too high. And then in the next $1 to $200 per month, then unknown, then greater than $200 per month. So there is a difference in the ratios of proportions of people defaulting in each of these groups. So that means checking underscore balance has some impact on a person defaulting the loan or not, right? So this is how we do EDA to select the variables. And I'm going to select few variables. So I'm going to ignore them. So I am going to ignore the rest of the EDA. So the columns that I am interested in my analysis, I'm going to select them. Months, loan, duration. For sure, this is important. Then amount. That's also important. We checked it. Checking underscore balance. We have one more variable called credit underscore history. And what other variables we can use? Purpose I am not going to use because it has a lot of values. Savings balance I am not going to use. Age and dependents and housing. So those are the ones I'm going to use. You may ask, how do I know? I have worked on this data set before. You should definitely do the EDA to figure out the variables that are important for you. Yeah, housing. Okay. And then finally, our target variable default. Okay, so these are the columns that we are going to use. So we are going to subset them. We are going to create another data frame df2. df2 is equal to slice the data frame 1. And what are the columns that we are going to select? The columns that we have just mentioned. Okay, now if you see df underscore 2 dot columns, those are the columns that we just selected for our analysis. So this is the target variable, and these are all going to act as our input variables. There's one more problem here. Let me explain that problem to you. Dot head. If you look at the problem, these two columns here, actually three columns, checking underscore balance, housing, and default, there are even credit history, there are categorical variables here. Now we cannot have categorical variables. Why? Just like how we used in linear regression, to predict y, we are going to say y is equal to some beta naught plus beta 1x plus something something so on. But if you say beta 1 into credit history is taking values like critical, good, poor. Now how can you use this character data into a mathematical equation? So for both linear regression and logistic regression, when you have character data like this, we need to convert that character data into some sort of dummy variables. And we will see what dummy variable means. Take housing. How many values are there in housing? So df underscore 2 dot, what is the column name? Housing dot value underscore counts. So this way you would get how many unique values are there and the frequency for each of them. For own, there are 713 observations. Rented type, there are 179 observations, and other 108 observations. So there are 3 values here. And let's convert this to dummy values. Let's see how we can do it. I'm not going to type them. I'll copy and paste from one of my earlier codes. It would be easy. And from this, we can change this. The variable for housing. So
your screen is not visible, sir.
1 second. Now?
Yes, sir. It is visible now.
Okay, fine. So we are going to create dummy variables for the column housing. So let's say dummy underscore housing is equal to, in pandas, we have a function called get underscore dummies. So I'm going to use that. And what is the variable which we are trying to create dummies? On the variable house. So this step is going to work like this. There are 3 unique levels in this column called housing. Now we are going to collapse this column into 3 separate variables. Let me explain how it actually happens. Now let's say we have this column called housing here. This is the name of the column. It has values like own, rent, other, own, etc. And these are like observations. We have many observations, so on. Now from this one column, we are going to create three columns. That's going to be like this. Housing underscore own, housing underscore rent, and housing underscore other. Wherever housing zeros. Rent is 1, so this will take 1, so others would take zeros. So converting a character once into binaries like this. Okay, wherever other is 1, these two will take zeros and this will be 1. Again, it is own, so this will be 1, these two will be zeros. So these variables, these three variables which are created from this one are called as dummy variables. The other name for them is one hot encoded variables. So either we call them as dummy variables or we call them as one hot encoded variables. Okay. So that's what going to happen to this variable now when we run this particular step. There is one more variable, that is credit underscore history, which I am going to convert into a dummy variable. So this is credit underscore history, and I'm going to give the suffix as history. So when we are creating the columns, we want the column to have a suffix of that. So housing underscore own, housing underscore rent, housing underscore other. So this suffix will tell what was the original variable and what is the newly created variable. And this is for, what is that one? That's for history. So let's name it as hist. And the third one, which we are going to create, is underscore balance. So we are going to create one more dummy for checking underscore balance. I would call this as balance. Now you get this one. Let's rename this as BAL. So we got three dummy variables and we are going to combine. It's like concatenating. I am going to concatenate df, which is the original data frame, and the three dummy variables that we have created. This is 1, this is 2, and this is 3. So we get 3 new columns added to it, and we create the new one, which is df underscore new dot head. Now look at, okay, it should not be df, it should be df underscore 2. Look at the columns we have: month loan duration, amount, checking balance, credit history, housing, default. These were the columns that were present in default already. And these are the new columns that we have created: house underscore own, house underscore rent, history underscore good. Closely observe this. House had 3 levels: own, rent, and other, but it has created only 2 variables, not 3. It should have been 3, right? But look at this statement: drop first is equal to true. So when we have 3 levels, we would always use 3 minus 1, that means going to ignore. So if a character column has k levels, the dummy levels are always going to be k minus 1. And there is a reason for it. These columns should be independent from each other. But if you have all the three, they are not meeting the criteria of independence. Now, if you know that this column is 1, others are zeros. If you know that these two are zeros, you obviously know that this one is 1. So they are not really independent from each other. So to avoid that situation, we would always use k minus 1 levels as dummy variables when we have k levels in the data. And that's the reason we got only two, house underscore own, house underscore rent. And we created dummy variables for history, and we created dummy variables for balance also. Once we have the dummy variables, we don't need these original variables anymore. Checking balance, I don't want it. Credit history, I don't want it. Housing, I do not want it. So I am going to drop them. df underscore new dot drop. What are the columns that I have to drop? This one, and then this one, credit underscore history, and then one more, which is housing. Comma, access is equal to 1. And then we are going to read. Look at the df underscore new, it should not have those columns. Those columns are gone. Now, except the default column, rest all of the columns are having numeric values. Okay? Yeah. We have some questions. Okay, if data quantity is not big. For 10 to 30 rows, you cannot use machine learning. Computers need, algorithms need a lot of data to learn from. 10 to 30 is like negligible. Even 1000 is very less when you really want to learn very well. For some sort of beginners, you can use observations like 400,000 and all, but generally 1000 observations itself is way too less. We would typically take in 10,000 or even more if available. If it's not available, that's a different case. It depends. Your second question, which talks about can we use machine learning for creating a trend of data and predicting the future data after certain time interval? There are two ways to do it. One way, when you are trying to predict something that is based on a time period, like 1 month down the lane. What would be the sales of my company by the month of July, by the month of August, by the month of September? We can do that. Those type of ones are called as forecasting, time series forecasting. That's a way to do it. Another way to do it is how you design your forecasting. So if we use machine learning, it depends on how we create our input data. And that's definitely a very big topic. How you, now if you look at this default variable here, it simply says whether a person is defaulted or not. But the person defaulted the loan after taking the loan maybe 6 months down the lane, 10 months down the lane, 15 months down the lane. When did the person default? That you don't know from this. So if you know how this is created, then I think they consider the time period also into the picture over here. So it depends on how you create the data also. Append is generally a method which is applicable in the on a list, but pandas data frame doesn't have a method called append. So if you see append, it is typically to append rows. It might have columns also. I don't know. Ignore index. It's generally for appending the rows, not for columns. Okay, and that's the reason I'm using concat. Yeah, though it has a method called append, it's typically for the rows, not for the columns. Yeah, if it can do columns, if there is a option, we can do that. Concatenate is doing it, so I'm going with concatenation. Your model might have a slightly different predictions. There could be many reasons for it. One, it depends on the variables that you have used. If you have changed the variables a little bit, it would. Two, when you selected your 80% data, your 80% means a random number generator is selecting that data for you. Depending on your system, your architecture, random number generators change. It also changes from one manufacturer to another manufacturer. If you have a different random number generator, you selected different data into your training. My training data could be slightly different. This particular problem happens with very small volume of data. We only had 400 odd observations. That's why when you take thousands of observations, this is not a big deal. It would not be so visible. But with very smaller data sets, the observations that went into your training data set would be slightly different than the one that I have in my training data set. Because of that also, the predictions would slightly different. May not be drastic, but some difference would be there. Smaller data sets, that's always a problem. Yeah, and that's another reason why you need to have large volume of data. You want your training to be consistent. When you do with smaller volumes of data, your training will not be consistent. It would change from one sample to another sample. But if you take a larger sample, it would be consistent. Okay, so 10 to 30 observations are not at all good when you want to learn. Okay, now we have good amount of data available here. Let's try to split this into training and test. So before that, we need to separate our data. So df underscore new, and in this we are going to select target. This is going to be default. So default is going to be our target variable, except default. Rest all of them are going to be our input columns. So df underscore new dot columns. So it would be easy for us to copy and paste. So these are all the columns that are going to be in input x variables. Input x variables is equal to df underscore new, and select all of this. Okay, except what variable? Default. Default should not be there because default is our target variable. That variable should not be in our input x. So we have separated them. Now x underscore train comma x underscore test, y underscore train comma y underscore test is equal to train test split. Oh, we did not imported it. Yes. From sklearn dot model selection import train test split. Here our input is input X, target is target, test underscore size is equal to 0.2 and random underscore state is equal to 1. So my training and test data sets are ready. Logistic regression, we call it as log, whatever the alias that you can give. And while training the model, input data is X underscore train, target is Y underscore train. Done. Just one single execution, a couple of lines of code, we have our model ready. Fine. Looks like we have some questions. Okay. Let's see how it predicts. I don't know how the predictions look like. We have a test data set kept separate. Let's predict. My predictions are log r dot predict X underscore test. So it has predicted. Now, how good is our model? How accurate is our model? Accuracy underscore score actuals Y underscore test predictions pred. It says your accuracy score is 0.73. So that means we are accurate 73% of the time. Not so good. Another way to look at the results is something called as confusion matrix. Again, originals actuals is Y underscore test. Your predictions is pred. So this is called as a confusion matrix. The confusion matrix is a very typical one. Let me explain that. We have our actuals Y and we have our predictions. Going to take values like noise. Sometimes they may not be same. Sometimes they might be same. Okay, like this. Now to compute accuracy, we only check if we are doing a good job, if they are same or not. So that's accuracy. But accuracy alone might not be very informative. So we are going to collapse this into a matrix like this. Actuals. Actuals can be no, can be yes. Predictions. Predictions can be no, predictions can be yes. If prediction is S, actual is yes, so we count that into this block here. If prediction is no and actual is no, we count that into here. If prediction is yes and actual is no, you count that over here. If prediction is no and actual is yes, you count that here. Okay, so that's called as confusion matrix. And there is a very confusion matrix are very important in the if you have to understand classification problems. Why? I see few people raising their hand. Unfortunately, I cannot talk to you directly. Please post your question on the chat window like others are doing. I will answer your question. So, if we predict an S, we predict no, it's called as negative prediction. And there is a reason for it. Okay, for example, if you take um, um, any diagnosis, COVID test. If someone takes the COVID test, if the test says positive, what does that mean? The person is infected. The person is having the virus. If the person is not infected, the test result is called as negative. So that's how, if we predict an event, so this is called an event. S is an event. If we predict an event, it's called as positive. If we predict a non-event, it's called negative. So tomorrow, if we predict it is going to rain, then it's called a positive prediction because we are predicting rain. So that's a positive. If we are not predicting, if we say there is not going to be rain, it is still a prediction, but it's called as negative prediction. And based on this, we fill this confusion matrix like this. If our prediction is positive, so this is positive, and actual is also positive. That means if it has happened, then it is called as true positives. If the prediction is positive, but it did not happen, that's called as false positive. On this side, our prediction is negative and it is true, so that's why it is called as true negative. Our prediction is negative, but it's not true, so this is called as false negatives. So this confusion matrix really helps us to understand how good the predictions are in a much better way. And that's why it is named as confusion matrix. No matter how many times you hear it is aptly named as confusion matrix, and there is a reason for it, right? Now, it would take a while for people to understand this logic of a confusion matrix. So this is our true positives, this is our false positives, this is our false negatives, and this is our true negatives. True negatives and true positives are good predictions, are correct predictions. These two, false positives and false negatives, these are error predictions. But in some cases, we might be more interested in true positives alone. True negatives, I don't care. Like if you predict that tomorrow it is not going to rain, it's a prediction, but it's not value. Why? In a year, there are 365 days. Out of 365 days, if you predict that you are going to be, there is not going to be rain on 300 days, you are always right, right? There are only few days where it is going to rain. Now, if you predict them accurately, that's very important for us. So predicting no rain is not a big deal. Predicting rain is going to happen is very important. So positive predictions are very important. Negative predictions are not. Okay. So to look at the model, if the model is really making good predictions or not, we always look at the true positives and false positives, false negatives. We don't care about true negatives. So that's the importance of a confusion matrix. If you want to learn more about it, it would take a lot of time. Yes, you can definitely infer it. Yeah, it can be represented graphically, and then you can use them. Okay, now comes the most important stuff. What is happening behind these two lines? That's very important for us. Let's go back. Let's try to use a simple example, like how we did in the case of linear regression. We have a input variable. So we have an input variable and we have a target variable. Only one input variable so that it would be easy to understand. So this is X and this is Y. Y can take values like 1 or 0 because here it's a binary data. Either it is a 1 or it is a 0. So there is no other options available. Let's take X as hours of preparation for an exam and Y as the outcome, like whether the person has passed or failed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, something like this. Number of hours they prepared versus whether they passed the exam or they failed the exam. To make the graph little more easy to understand, I am moving 0 a little up. 0 should be here, but just that we move the 0 to a little up here so that it would be easy to understand. Now, lot of people who prepared for less number of hours, most of them failed the exams, and a couple of them, though they prepared for less number of hours, they are able to pass the exam. And a lot of people who prepared well, that means who prepared more for the exam, has definitely passed the exam. So these are the people who prepared for more hours. And some people, though they prepared for more, they still failed the exam. Okay, this is how we can represent X and Y in this particular case. Okay, X is our number of hours of preparation and Y is the target variable. In case of linear regression, just for the comparison, we represented the relationship between X and Y like this. So Y is equal to AX plus B, or in other words, we write Y hat is equal to beta naught plus beta 1 into X. This is a linear relation. But here, unfortunately, we cannot write the same equation. So if you write Y hat is equal to beta naught plus beta 1 x1, it would look like a line which is going through this like this. But that's not the best line. That line doesn't represent this data. There is no way that we can represent the relationship between X and Y here using a linear line, right? So instead of a linear line, we want to represent the relationship between X and Y with a slightly better one. And let's see what that is. Now, if we can represent the relationship between X and Y using some sort of equation like this, where when X is small, this line is taking very small values, and when X becomes large, so this line is going to take large values. So we need to have a function which is probably defining this particular shape. It should always take values, it should always give an output between 0 and 1. For smaller values of X, the output should be very close to 0. For larger values of X, the output should be close to 1. So what could be the equation, or this is called as sigmoid function. So sigmoid functions take this type of shape. So we can represent this as Y hat is equal to 1 by 1 plus e to the power of minus x. So this is called a sigmoid function. And we are going to represent the relationship between X and Y using this sigmoid function. Now, think of a large value for X, 1 divided by 1 plus e to the power of, let's say, 10. Now it is minus 10, right? So e to the power of minus 10 is 1 by e to the power of that, which is almost going to be 0.00000 something. So 1 by 1 plus 0.0000 would take a value when x is large, your y hat value would be close to 0.9999. When x is very small, let's say we take x as -2, 1 by 1 plus e to the power of -2, that is e to the power of 2, e square, 2.7 square, which is going to be, let's say, 6 something. 1 by 6 plus 1 by 7, it's much more closer to be 0, right? When x is small, y hat would be very close to 0, okay? So output of this would always be going to be between 0 and 1. No matter whatever the value of x you give, it is not going to deviate from this. So that's why we are going to use this sigmoid function to represent the relationship between using x in the form of a linear equation like what we did yesterday. We are going to predict the value of y using the sigmoid function. So for logistic regression, the prediction of y hat is given by 1 plus 1 by 1 plus e to the power of minus beta naught plus beta 1 x1 plus beta 2 x2 plus so on beta m xm. So this is going to be the equation. And what do we want to find out? We want to find out the values of beta naught, beta 1, beta 2, all the way up to beta m. So if we could find the values that satisfies this data, then we can use the values of beta naught, beta 1 and the input variables x1, x2 to predict the value of y. Our prediction of y in this case is always going to be between 0 and 1. So let's call this as a probability. Now, because we have a probability, our prediction is always going to be between 0 and 1. So you need to choose a cutoff. Let's say 0.5 is the cutoff. If it is less than 0.5, you would consider your prediction into 0. If it is greater than or equal to 0.5, then your prediction would be considered as 1. Why? Your actual values are going to take values like either 0 and 1. There is nothing like a probability there. But the output of your logistic regression is always going to be a probability. So because it's always going to give you a probability, we are going to use the cutoff of 0.5 to say if the probability is greater than 0.5, we would consider the category, we would consider the class into 1. And it doesn't always have to be 0.5. We can change this, but you need to understand a lot of other concepts to decide what could be the right cutoff. And that's definitely beyond the scope of the discussion because it involves a lot of other concepts. So to understand this very well, you need to definitely have a probability refresher, and you probably could also have a good understanding on odds and ratios. Then you would know what is the right cutoff to choose. And building a model, let's say writing these lines of code, is probably the easiest of the tasks that we do as a data scientist. But there are a lot of other things that we have to consider to make the predictions that we are making useful for the business. That's where the experience of a data scientist comes into the picture. If it is like writing these hardly 20 lines of code, anybody can do it. Then what is the complexity in data science? That's not the complexity. The complexity is understanding what happens behind the scenes, understanding the probability distributions, and based on that, you need to derive what is the best way of using it. So that's where, as a data scientist, you would have to spend a lot of your time. Okay, fine. one more thing we have to answer. What is the cast function? Yesterday, what was the cast function that we have used in here? You cannot use the cast function ordinary least squares. Why? This is going to give you a value between 0 to 1, and you cannot square them, because if it is 0 0.1, if you square it, it becomes 0.001. Handling it with ordinary least squares is not at all feasible. Okay, so instead of using ordinary least squares in logistic regression, we use another cast function that is called as maximum likelihood, and a modified version of it we call this as negative log likelihood. So if someone asks, hey, what's the cast function between that we use in logistic regression? The cast function is negative log likelihood. Okay, negative log likelihood is very tricky to understand for the beginners. So I would give you the likelihood equation and we would stop with likelihood itself. As you read more about it, then you can easily understand what is the negative log likelihood. The likelihood equation is like this: yi into pi plus 1 minus yi into 1 minus pi. So this is called as likelihood equation. Now let's say we have y like this 1 0 0 1, and we have p1 p2 p3. P1 p2 p3 from model 2 and p3 came from model 3. P1 is like this 0.9 0.1 0.1 0.9. P2 is like this 0.8 0.2 0.2 and 0.8. P3 is 0.7 0.2 0.3 0.8. Now out of P1 P2 P3, which one you think is very close to y? I'll wait for the answer. Think of it. P1 is a set of probabilities. P2 is also a set of probabilities. P3 is also a set of probabilities. Out of P1, P2, P3, which one you think is very, very close to your y? P1, right? Yes. Why? Look at the difference between the P1 and y. It's all when y is 1, probability is 0.9. When y is 0, probability is 0.1. Because we have only 4 observations here, we could easily say, okay, P1 is better representing the y. That's called likelihood. The likeliness of a probability distribution representing the actuals. How likely this probability distribution is representing your y, and whichever is giving you the maximum value, that is the one which is representing your y in a better way. So that is why maximum likelihood. And let's compute it for all of this. For the first observation, yi is 1 and pi is 0.9. 1 minus yi will become 0. So 0. So 0 into anything would be 0. 1 minus yi would be 1, and 1 minus pi. Pi is 0.1. 1 minus pi is 0.9. So for the next observation also it is 1 into 0.9 plus 1 up, next one is also 0.9. Okay, so this is going to be 3.6. For the next one, 0.1 into zero point 0.8 plus again 1 into zero point 0.8 plus 1 into zero point 0.8 plus 1 into zero point 0.8. So this is 3.2. For the third one, 1 into zero point 0.7 plus 0.8 plus 0.7 plus 0.8. So this is 3. So whichever gives the maximum value for the likelihood, that is the one which is representing your y in the most appropriate way. So for P1, the likelihood is 3.6. For P2, the likelihood is 3.2. For P3, the likelihood is 3. Now, P1 is the one that is giving you the maximum likelihood. So we could say P1 is a better representation of Y. Now, this is the likelihood equation. Whichever gives the maximum value for that likelihood, that is going to be the right representation of your data. Now, in this, let's submit our, let's say we have X and Y. Preparation for exam 5 hours passed, 2 hours failed, 6 hours passed, 5 hours failed, and 2 hours passed, something like yi is 1. Then pi is nothing but the probability, which is going to be 1 by 1 plus e to the power of minus beta naught plus beta 1 into 5 plus yi is 0 here. So this is like 1 minus yi, which is 1 into 1 minus pi. What is 1 minus pi? 1 by 1 plus e to the power of minus beta naught plus beta 1 into 2. For the third observation yi is 1. So it is going to be 1 by 1 plus e to the power of minus beta naught plus beta 1 into 6. For the fourth observation, 1 minus 1 by 1 plus e to the power of negative beta naught plus beta 1 into 5 plus the last observation, 1 by 1 plus e to the power of negative beta naught plus beta 1 into 2. This is our cost function. And we want to find out the values of beta naught and beta 1 in such a way that this cost function takes the maximum value. Yesterday, we want to find out the values of beta naught and beta 1 in such a way that the cost function takes the minimum value. Today, we want to take the values of beta naught and beta 1 in such a way that this cost function takes the maximum value. Why? Because that is the best representation of y. So yesterday we did minimization for ordinary least squares. Today we are going to do the maximization for the log likelihood. So for doing maximization, you need to take the partial derivatives second order, not the first order, right? So we need to do dou by dou beta naught. Again, we need to do dou by dou beta naught, which is going to be little tricky. So to avoid that, a modified version of it is used, which is called as negative log likelihood. So in a negative log likelihood, this is what we are going to do our this one. Why? When you are deriving yi into pi, this is very difficult. When you have a product in the derivative a into b, you have to use the Euler's rule, which is going to be something like dou by dou x of f of g of x. This is like two functions within themselves. So these are very tricky. So to avoid that, if we take log, What happens if we take log of AB? It becomes log A plus log B. Now the product is gone. It is in the form of linear. So we take log of the likelihood, which is yi into pi plus 1 minus yi into 1 minus pi. So to avoid the product in the derivatives, we are going to take the log of the equation. Second, maximization is always a problem. Minimization is easier. So we don't want to maximize this. So if we put a negative before this entire equation, this becomes negative log likelihood is used as the cost function in logistic regression. Of course, that's a bit of heavy math involved over there. There is probability concepts, there is linear algebra concepts, and there is also maxima minima, which is calculus. All of this is definitely the strength, the backbone of data science. If we just look at these statements here, they do the job for us, but we don't appreciate what happens behind the scenes. So if you know what is happening behind the scenes, so much of sound logic is being used in coming up with those estimates of beta naught, beta 1, beta 2, and finally to make the prediction. That's where the strength of a data science is. It's good to know, but it's going to take some time. As a beginner, you would probably not start with all of these at a time. We always take a top-down approach, like first learn how to use the built-in functions to learn from the data and make predictions like this and check if the predictions are okay or not. This is the first step, the top step. Second, once you know how to do it, when you are very thorough, what is required to come up with predictions, the second step is to understand how we are able to come up with the predictions. So what is happening behind the scenes here? And the final step is trying to understand all the math involved in it. If you know the math involved in it, you get pretty good knowledge about each algorithm. You know that how the algorithm is working. An algorithm or not, if you have to use it, how to get the best out of it. So that is the mastery level. To reach the mastery level, it would probably take you a year or so. Begin with the top, how to make use of these existing functions to come up with the predictions, then understand what's happening behind the scenes, and the third level is mastering the math behind it. It's going to take some time, yeah, but that's the highest level that you have to reach. Okay, that's all about logistic regression. Now let's jump into the next one, decision trees. Okay, let me take a pass. Any questions on this so far? Are you able to really understand what really happened behind the scenes in logistic regression? Do you think that's informative? Okay, a lot of people saying yes. If you raise the hand, I will not be able to understand. Okay, good. Looks like there are significant amount of people who understood this. Books, I don't know, because I'm not a book guy. I haven't read a book in the past few years. When I learned it in 2008, 2009, that's where on data science now. It's about learning from different sources. No book can give you all the information that is required. I cannot. I at least don't know any book that has exhaustively explained everything in it. Okay, you learn from so many different sources. You learn from blogs. You learn from some tutorials. You learn from some workshops like this. Then you try to use them. You try to master them. Nobody can become a data scientist in a day or two, or even for that matter in a month. It's a very long journey. It would probably take a year for someone to reach to a stage where they can claim, yes, I am a data scientist now. I can do data science stuff, right? So that's how complex these things are. And it's always going to be slow, but it's always very rewarding if you put that effort. Okay, next let's jump on to data analyst. What does a typical data analyst do? Data analyst never do any type of predictions. They can aggregate the data. So if you go and ask a data analyst this question, hey, what was the sales in the last 1 month? They can go to a database, query the database, tell you what is the sales by product, by region, by doing so. But if you ask the question, what would be the sales next month? Can you predict it? The data analyst would say, sorry, I cannot do that. I don't have that required knowledge. So this is where a data scientist comes into the picture. Looking at the historical data, learning from it, we should be able to make a forecast. We should be able to data mining is typically on both the sides of it. Data mining in the regular industry is typically called as slicing and dicing. Okay, look at sales. Why is our sales bad? What happened in the last month? Let us look at the sales by region, by product. So you slice and dice the data to get to a point and identify the root cause of our problem. Okay, our sales are less because this region, Europe region, did not perform well in the past 3 months. Our sales are down because one of our fast selling product did not sell good in the last 1 month. Now you identify the problem and now you need to overcome that. So what we can do, can we promote this product? Can we increase the marketing on this product? Can we see what is the problem with Europe region? Why the sales went down in the Europe region in the past 1 month? Was there any change in the sales teams? So this data mining is trying to go back into the historical data, trying to slice the data, pick up the root cause of the problems, interpret it, and take some actions. But the actions always comes from domain knowledge. A leader, a sales leader for Europe region will now see, okay, there is a sharp dip in the sales in the Europe region. Let me think of a strategy how I can improve the sales in the next 1 month, in the next 1 quarter. So what decisions they make is purely based on their domain knowledge, right? So data mining is breaking down the data into silos, slicing and dicing it. But data science is foreseeing future. Depending on what we have seen in the past, what would happen into the future. And we are always going to predict the things. In data mining, also, there is nothing much of a prediction. It's all about their thinking. It's all about their strategy. But data science is all about prediction. Okay. Now, let's try to see an example for decision tree. And I'm sure all of you are going to absolutely love it. What happened? I accidentally closed my notebooks. Let's create a new one and name it as decision tree. Import pandas as PD. Import numpy as NP. I'm not going to do any visualization here, so I'm not importing matplotlib and cbon from sklearn dot e. One second. Import decision tree classifier. One is called as CART, classification and regression trees. We will see what is the science behind it in a little while. And the name itself says these decision trees are capable of producing both classification as well as regression. From sklearn.metrics, import accuracy score, comma, confusion matrix. That's all. Good enough. Let's read the data. We call this as credit is equal to, I'm naming the data frame as credit, pd dot read underscore csv, credit dot csv. We did not run this step. Target is equal to credit. I am not doing any EDA. I'm directly going to jump in to building the model. Default. Okay. And rest of the columns should go into input variables. Credit dot columns. Let's try to put all of this input all is equal to. So these are all going to be our input columns except this one here. To remove one more variable here, purpose. It has a lot of values. It would make so your input x is equal to credit and input calls. So except default, these are all the columns that are going into input calls. X underscore train, X underscore test, Y underscore train, Y underscore test is equal to train test split. We did not call it. From sklearn dot model underscore selection, import train test split. Good. Now train test split, input x, target test underscore size is equal to 0.2 and random underscore state is equal to 1. dt is equal to, this is an alias, you can give any name to it, decision tree classifier, dt dot fit x underscore train, comma y underscore train. says did not convert. Okay. Yeah, we forgot one step. We have to convert them to dummies. Should not be the case. It should work without. Whoever is raising hand, please post your questions so that we would. I would be able to answer the questions for you. When you are raising your hand, I don't know whether you have a question or you did not understand, or is there something else? No questions? Okay, then let's continue with this. Let's see if we can check this one out. First, to cause error, we will change this. It is expecting us to convert this to dummies. We created most of them to dummies. That's a lot of variables there, but that's okay. Right. Now we are going to use this target, everything fine. Okay, it ran. It looks like we have a question. Am I audible? Any issues with my audio?
No, sir, it's audible.
Okay. So we trained the model. Model is ready. Now let's see how the model predicts. My predictions is equal to, we call this as dt dot predict, and we are going to predict on x underscore test. Our predictions are also ready. Accuracy underscore score. Original is y underscore test. Prediction is this. Wow. Accuracy score is 1. Surprised. It gave perfect predictions. Let's look at confusion matrix. If it is true, that's too good to believe. Yep, no false positives, no got 100% accuracy. And this is a magic, okay? It might not happen every time. 100% accuracy is generally not seen at all. This is a sample, simple training data, practice data sets. So that's why you could probably see 100% accuracy, but this may not be the case all the time. But anyway, decision trees are always very, very beautiful in the way they are working. So we got a score of 100% accuracy here. Amazing. Now, all of the magic, if you remember, in linear regression and logistic regression, we perform some EDA, we select some variables by looking at the relationship between the input variables and the target variable. If the relationship is strong, we select them. We do a lot of things in linear regression and logistic regression. Linear and logistic regression came from the concepts of statistics. They are slightly different, but decision trees came from the concept of data mining. They are very, very powerful and they are very easy as well. Now, you do not have to do any of those things which we did previously. What we did, we read the data, we separated the target column, we separated the input columns, and we created the dummies for the input columns. We divided that into train test split. Some magic happened here in these two lines. And finally, we got our predictions out. And it looks, when you look at the accuracy, it's amazing, 100%. How does it really work? So the decision tree algorithm works like this. The algorithm in question here that we are trying to learn is called as CART. Within decision trees, there are a lot of different algorithms. CART is probably the most heavily used one of all. So that's why we are looking at CART here. So what happens in a decision tree is like this. To start with, let's say we have 1,000 observations, all 1,000 observations here, and your target variable y can take values like 0 and 1. Out of the 1,000 observations we have, 1,000 observations we have, let me put this in a slightly different way. So the 1,000 observations we have, 70% of them belong to no class and 30% of them belongs to S class. At the root node, when we want to, our objective is to separate the observations that belongs to S class and the no class. And we have input variables like this. Let's say we have input variables x1, x2, x3, x4. So these are our input variables. Using these input variables, we want to separate these 1,000 observations into yes and no. Most of the trees works on the principle of recursive principle behind the decision trees. Of course, some of the trees work beyond binary partitioning, but most of the tree-based algorithms works with binary partitioning. This one here is called as the parent node. At the parent node, the ratio, the proportion of yes and no is 70% and S is 30%. So this is like 700 observations here through 300 observations here. Let's say we split this 1,000 observations into two smaller nodes. These are called as the child nodes. So the child on the left hand side, this is the child on the right hand side. We are going to separate these 1,000 observations into two. Let's say we got 600 observations here and we got 400 observations here. Now, the first question is, how did we get 600 observations here and how did we get 400 observations here? So this separation is going to be made using a split criteria. Let's say
we use a split criteria, which is like this. If x1 is less than 10, if it is yes this side, if it is no this side. Okay, we have an input variable x1. If x1 is less than 10, those observations will go into the left hand child. If the x1 is greater than or equal to 10, those observations will go into the right hand child. Of course, there is also a question here. Why only x1? Why not x2? Why not x3? Why not x4? That's a question. Yes, that's a why not x1 less than or equal to 5? Why not x1 less than or equal to 8? Some different criteria can be used to split the data, right? How did we choose x1 and how did we choose x1 less than or equal to 10 to split the data? That's a question that we want to answer. We will answer. Now, out of the 600 observations that we got here, let's say 100 observations belong to S and 500 observations belong to no. Now, out of the 300 observations we got, or 400 observations that we got here, let's say we got 200 observations that belong to yes and 200 observations that belong to no. Look at the proportions of the observations at the parent node, 70-30. Here it is on the left hand, on the right hand side it is 50-50. On the left hand side it is 500 by 600, which is like 5 by 6. And on the, for the no category it is 100 by 600. Now compared to the parent node, the separation of S and no observations in the child node is better or not. How do we decide? So we have to understand something called as a measure of impurities. So we are going to use this metric to decide if the proportion of S and no observations in the children are better than the proportion of observations between S and no at the parent node. The commonly used measures of index. So these are the measures of impurity. Now let's see what entropy is and how entropy works. Let's say we have 5 observations here, 5 observations here. This is no, this is yes. So this is your parent node. Now, to measure the impurity at this node, we use this neg sigma negative log of P by T to the base 2. So this is how we measure entropy. Pi, I is equal to 1 to K and K is equal to 2 here. I'll write them. Minus log of, sorry, Pi by T, my mistake. Too many things to remember. I don't have that much memory power these days. Minus sigma Pi by T log of Pi by T to the base 2, where I is equal to 1 to K, where K is the number of classes. Here it is 2 classes, no and S. Right. So for the parent node, the value of entropy is going to be measured like this. Five by 10, that is minus, into log of 5 by 10 to the S group, minus 5 by 10 log of 5 by 10 to the base 2. So this can be written as 1 by 2, 2 to the power of minus 1. So 2 to the power of minus 1 will come here. So this will become 1 by 2. Log 2 to the base 2 will be 1. And here also 5 by 10, which is 1 by 2 into log of 2 to the power of minus 1 to the base 2. You send this 1 here. So this becomes plus. Log 2 to the base 2 will become 1. So 1 by 2 plus 1 by 2, 1. So the entropy at the parent node, at the root node, is 1. If, let's say, the root node is something like this, 0 and 5. 0 for no category and 5 for S. In this node, all of them belong to S category. So there are no observations for the no category at all. What would be the entropy of this? Minus 0 by 5 log of 0 by 5 to the base 2. Though it is undefined, this becomes 0. So I'm going to remove this. Minus 5 by 5 log of 5 by 5 to the base 2. So this is 1. Log 1 will be 0. So the overall value is 0. So entropy is going to take values between 0 to 1. For an impure node, when it is 50-50, it is going to take a value of 1. When 5 for no category and 0 for S category. So for both the cases, your entropy will be 0. If entropy is 0, that means the node is a pure node. If entropy is 1, the node is the impure node. Okay, so that is why entropy is called as a measure of impurity. And here we are using the entropy to find out what would be the purity of this node. At the parent node, entropy for this is 1. At the parent, if this is the node, the entropy at the node is 0. Next, another one is called Gini index. Now, let's see how to compute Gini index. 5, 5, both belongs to, both has 5 and 5. Sigma pi by t whole square, sorry, 1 minus sigma pi by t whole square. Now let's see what is the Gini value for this particular node. 1 minus 5 by 10 whole square minus 5 by 10 whole square. So this is 1 minus 1 by 4 minus 1 by 4.5. So for a perfectly impure node, Gini is taking a value of 0.5. And for a perfectly pure node, which is going to be like this, 0 for no category and 5 for S category. Zero by 10 whole square. So this is 1 minus 1 by 2 whole square. 1 second. Which is 1 by 4, which is going to be 0.75. That's not right. I made maybe a mistake somewhere over here. Oops. How come this is 5 by 10? It's 5 by 5, right? So this is 0 by 5. That's why. 5 by 5 is 1. 1 square is always going to be 1. 1 minus 1 will going to be 0. For a perfectly pure node, your Gini is going to be 0. Entropy is going to take values between 0 to 1. 0 means pure, 1 means impure. And Gini going to take values between 0 to 0.5. 0 means pure and 0.5 means impure. Most of the old days algorithms used entropy as the measure of impurity. This is deprecated now. Almost all the latest algorithms use Gini index as the measure of impurity. Why? Computations are faster with Gini. It's just a ratio and squares. So this is simple linear calculations. But here you have log to the base 2, so it has to make a lookup every time. So this is time taking. So that's why that are used in the latest algorithm. Now you know what entropy and Gini is. Now let us answer this question. Now you have, let's say, 6 and 4 here. We want to divide, we want to separate this into 2 nodes. And we got 3, 2 here, and we got 2, 3 here. What is the Gini at the root node? Let's say the Gini at the root node is 1 minus 6 by 10 whole square minus 4 by 10 whole square. It's almost close to 0.5. Let's say this is 0.43 something. I'm roughly computing it. Here you have Gini on the left hand side and Gini on the right hand side. Gini on the left hand side, which is going to be 1 minus 3 by 5 whole square minus 2 by 5 whole square, and here 1 minus 2 by 5 whole square minus 3 by 5 whole square. Let's say this is 0.43 and this is also 0.43. Now the resulting Gini at the child level is a weighted average of this. So 0.43, how many observations we have on the left hand side? So into 5 by 10. And what we have on the right hand side? 0.43 into 5 by 10, which is also going to be 0.43 only. The impurity at parent node is 0.43 and the impurity level at the child node is also 0.43, meaningless. Split something like this, where we got 6 observations here, where we got 4 observations here. All 6 belongs to no class and 0 belongs to S class. All 0 belongs to no class and 4 belongs to S class. So what is the impurity at the root node? 0.43 parent node. What is the impurity at the child node? Left hand child 0, right hand child 0, weighted average of it 0 into 6 by 10 plus 0 into 4 by 10 is also going to be 0. Look at the decrease in the impurity from 0.43, it becomes 0. So that means this split is very good. This split was not able to separate the S observations and no observations, but this split was able to separate the S observations and no. Now, this is exactly what we are going to use in deciding what is good when we want to separate the data. Let's say we have a root node like this, where we have 1000 observations and 700 of them belongs to no class and 300 of them belongs to S class. We are separating them into 2 nodes. child nodes, left hand side, right hand side. We are doing it with x1 here, and we are doing this again with 700, 300, no, yes, separating this into child node, and we are doing with x2 here, and we are doing same 700, 300, no s. Now we are splitting this with x3 here. At the root node, let's say our entropy is 0.42, sorry, Gini is 0.42, Gini is 0.42. When we split this with x1, it is giving us an entropy of 0.2 on the left hand side and 0.1 on the right hand side. So this is 0.2. Let's say we got 600 observations here and we have 400 observations here. Sorry, 800 observations here and 200 observations here. So 0.2 into 800 by 1000 plus 0.1 into 200 by 1000. So this is going to be roughly between 0.2 to 0.1. So it's like, let's say 0.18. So this is the entropy, sorry, Gini at the childs when we used x1 to split. If we use x2 to split, let's say this gave 0.3. And if we use x3 to split, let's say this gave 0.3. To the maximum extent among these three variables, x1, x2, x3, obviously x1, because it is giving you the least value of Gini compared to the parent node. That's what exactly a decision tree does. It starts with a root node. It has so many input variables, and it takes all possible split points available in that variable. Split points are generally decided by percentiles. 10th percentile, 20th percentile, 30th percentile, all the way up to 100th percentile. 10th percentile. If we split with the 10th percentile, what is the resulting Gini in the child nodes? If we split with 20th percentile, 30th percentile, 40, what is the best of the Gini observed? That is the best split point in x1. Repeat that for x2, repeat that for x3. Now you have the best split point with x1, which is giving you a Gini of 0.18. x2 is only giving 0.3, x3 is only giving 0.34. And that's how it decides at the root node whichever variable gives the maximum difference between the Gini of the root node with the Gini of the child node, that variable will be allowed to make the split. And this process would be repeatedly performed. For example, let's say this is our root node. Then let's try to split this using x1. We got 2 children. And we do this again. This becomes our new parent node, and we are going to split this further. Let's say we are splitting this with x4 here, and we are going to can decrease the Gini from the parent to the child node. These steps will be continued. If we cannot decrease the Gini from the parent to the child, if the parent is 0.1 and if the child is giving 0.12, this is not allowed, it stops there. So as long as the Gini can be decreased from the parent to the child node, it proceeds. And when it stops at some point, that's where we call this, the tree is completed. This is your root node. These are your leaf nodes. In this tree, root is at the top and leaves or decision nodes are at the bottom. Okay, and that's a tree-based algorithm. I know we are at the top of the hour. We would start tomorrow, and I would briefly explain this tree process again. and how we use this tree to make further decisions. Now, you get a new observation. You pass the new observation to the tree here. You check if x1 is less than 10. If it is true, yes, this side. Then you check if x4 is less than 2. If it is yes, this side. And finally, your observation lands here. All the observations landed here belongs to no class. So your prediction is also going to be no class. So that's how the tree learns from the training examples by recursively partitioning them into binary partitions. And from that, it is going to make the predictions. Okay. Yeah. Tomorrow we have a smaller topic. This, and we continue with the clustering slightly later. I know that that's a lot of information over there. You don't, yeah, you can, in a way, you can go to the source code of all of this. What happens in the decision tree, you can go to the sklearn model, you have that installed on in your machine. So you go to your Anaconda, you go to your Python libraries, and you can search over the sklearn and select them and look at the source code. The source code is already available with you. Okay. I know that's a lot of information over here, and it's definitely overwhelming for a beginner. And trees are so wonderful because you don't have to tell them what variables to use. They are deciding what variables to use, what variables not to use. That's the beauty of a tree. They select their own variables. As long as a variable gives that improvement in the Gini, decrease in the Gini, they are used to split the data further until it separates all the yes and no classes, or there is no further possibility of decreasing the Gini. That's where the tree stops and says, hey, my learning is done. I am a tree now. You can use me for decision making. Give me an observation. I will check which leaf node it is going to fall into. In that leaf node, whichever is the majority of the observations, and my prediction is going to be same. Okay, yeah, we will stop here. We would continue with a slightly more deep dive into the tree tomorrow, and then